In the first problem, they tell us that the frequency, well, first they tell us off that brown rabbits is dominant, and then white rabbits are recessive. And they also tell us that the frequency of the homozygous recessive genotype is 0.35. So that's the information that they've given to us. Now, if we remember our formulas, this formula, p squared plus 2pq plus q squared equal to 1, this is when you talk about the different individuals. So homozygous dominant, heterozygous, or homozygous recessive. Well, here they straight up told us homozygous recessive, how the frequency of those individuals is 0.35 or 35% of the population. So that's the information that they've given us so far. And we know that homozygous recessive is equal to q squared. So our q squared is equal to 0.35 for this problem. Now, for part A, it asks us, what is the frequency of the heterozygous rabbits? For heterozygous rabbits, that's 2pq will tell us how often or what percentage of the population is heterozygote. For that, we need to find p and q. So I'm just going to go to the side here. If I know q squared is equal to 0.35, then I'm going to have to take the square root of both sides in order to get q. So when I do that, I find that q is equal to 0.59. That would mean that p is equal to 0.41. So if I want to find the heterozygote frequency, or what percentage of the population is heterozygote, I'm going to do 2 times 0.59 times 0.41, and you just multiply that across, and you get that is 0.48. Now what that really means is 48% of the population is heterozygous. For part B, it asks us what's the frequency of the dominant allele. Well, that's just p. And then for part C, it asks us what is the frequency of the little b, or the recessive allele. That's q. Because when our formula p plus q is equal to 1, these are talking about allele frequencies. So this is the dominant allele, and that's the recessive allele with p and q. So let's go ahead and look at question number 2. So this is a population of birds, contains 16 animals with red tail feathers and 34 animals with blue tail feathers. Blue tail feathers are the dominant trait. So I'm going to write down the information given to me. I have red phenotype, which is the recessive phenotype. And I have blue, which is the dominant. And when I read about this, it says a population of birds contains 16 animals with red feathers. And then I have 34 with blue. So my total population is 50. Now, I can find here, if I know 16 of the animals have the recessive phenotype, and the total population is 50, this is basically telling me q squared, because these are the individuals with the recessive phenotype. So 16 out of the population have the recessive phenotype, meaning they'd be heterozygous, homozygous recessive, out of my total population. So when I do the math and I divide 16 divided by 50, I get that my q squared is equal to 0.32. So far that is what is given in the initial question. So part A asks us, what is the frequency of the red allele? Well, the red allele is recessive, so that's asking for q. And so I'm just going to take the square root of q squared. Q squared was 0.32. So I take the square root of both of these. I get that q is equal to 0.57. And then for part B, it's asking me what is the frequency of the blue allele. So that's my dominant trait, which is P. So I'm going to take the formula P plus Q equals 1. And in this, I know that P plus 0.57 is equal to 1. So then I can subtract 0.57 from both sides. And I get that P is equal to 0.43. And then what percentage of the population is heterozygote? So I would do 2PQ. 2 times P times Q tells me the frequency of heterozygotes. So I go 2 times 0.43 times 0.57 and enter that into my calculator. And that should tell me 0.49. So 49% of the population is heterozygous. Now, what percent of the population is homozygous for the blue allele? So P squared is what represents our homozygous dominant individuals. So I would take my P squared, 0.43, and square it. And that gives me about 18% of my population. So 0.18 is my answer. In percentage form, it's 18%. Now, if I was really curious and wanted to double check myself, what I could do is look back at the formula P squared plus 2PQ plus Q squared is equal to 1. And I found that P squared is 0.18, 2PQ is 0.49, and Q squared is 0.32. Now when I add those up, I see it equals about 0.99, and that's just because of rounding errors. So really my calculations work out. And when I look at what this all actually means, it tells me about 18% of my population is homozygous dominant, 49% of my population is heterozygous, and about 32% of my population is homozygous recessive. So let's go on to number 3. So number 3 says about brown hair and blonde hair. It's 168 people with brown hair, which is the dominant trait, out of a population of 200. So what is the predicted frequency of heterozygotes, homozygous dominant, homozygous recessive? So they're basically asking us for each part of this formula, P squared plus 2PQ plus Q squared equals 1. Well, of course, we have to start with P and Q before we can solve any of this. So always start with Q. Well, they gave us our number of dominant individuals. So then if I'm looking for, well, how many are my recessive blonde? Well, if I have 200 total, 168 are dominant, that would mean 200 minus 168 will tell me how many have the recessive phenotype. So about 32 have the recessive phenotype of blonde. So if I have 32 out of 200, those are my number of individuals that are recessive, or my Q squared. If I type that into my calculator, I should get about 0.16. So my Q squared is equal to 0.16. So right away I can answer. Now, part C is 0.16. Now if I look at solving for Q, I'm going to take the square root of both of these. And I find that Q is equal to 0.4. And therefore, because P plus Q is equal to 1, I have P plus 0.4 is equal to 1. I know that P is equal to 0.6. So if I were to look at part A, I go 2 times 0.6 times 0.4 equals 0.48. So my frequency of heterozygotes is about 48%. And then for part B, homozygous dominant, I'm going to do p squared. So that is equal to 0.6 squared, or 0.36. So my answers here, even though they got kind of hidden in this, my frequency of heterozygotes is 48. My frequency of homozygous dominant is 0.36, and my frequency of homozygous recessive is 0.16. Now going on to more questions. Number 4 is asking, says 98 out of 200 individuals in a population express the recessive phenotype. What percent of the population are heterozygotes? Okay, so it doesn't tell us any of the traits, but we do know homozygous versus homozygous and heterozygous. So I have 98 are recessive phenotypes. And my total population is 200. So basically they gave me Q squared. So if I do the math, I find that Q squared is equal to 0.49. And so if I take the square root of both of these, I find that Q is equal to 0.7. And because P plus Q equals 1, P is equal to 0.3. So my question asks me, what percent of the population are heterozygotes? 2 PQ are my heterozygote, so it's 2 times 0.3 times 0.7 should be 0.42. So 42% of my population are heterozygotes. Looking at number 5, there's data on the Basques from Spain, which show that 230 of them were Rh positive and 170 were Rh negative. Calculate the allele frequencies of the dominant and recessive alleles. Okay, so let's write down our information first because there's a lot given to us. So we know that dominant is going to be Rh positive and recessive is going to be Rh negative. And we also know that out of our 400, 230 were Rh positive and 170 out of 400 were Rh negative. So when I look at this, they're asking me for my allele frequencies of my dominant and recessive. And so because it asks for the alleles, that's P and Q. So we're looking for P and we're looking for Q. So when I do this, I know that 170 are Rh negative. And from reading the question, I know Rh negative are my homozygous recessives. That's my Q squared. So my Q squared is equal to 170 divided by 400. And I find that my Q squared is equal to 0.425. Now if I want to solve for just my Q, I'm going to take Q squared is equal to 0.4. I'm just going to round to 43. I find the square root. And I find that my Q is equal to 0.66. And when I find my P, P plus Q is equal to 1. So my P is going to be 0.34. So they asked me for my allele frequencies, dominant and recessive, and so here they are. Now the second part of the question asks how many of the Rh individuals would be heterozygous? 2PQ. So I go 2 times 0.34 times 0.66. And I have about 45% of my population. It's 0.45 or 45%. My population are heterozygous. If we're looking at number 6, here I have in 1 in 1,700 U.S. Caucasian newborns have cystic fibrosis. Capital C is the normal allele, dominant over recessive. Individuals must be homozygous for the recessive allele to have the disease. So right there, that information tells me little c equals cystic fibrosis. What percent of the above population have cystic fibrosis, or Q squared? That's easy. 1 out of about 1,700 have cystic fibrosis, and that's my homozygous recessive individuals. So when I do this, I find my Q squared is 1 divided by 1,700. It was a very small number. So let me use my calculator. We get 0.00059. And so this asks what percent of the above population. So this is not in percent form. To get this into a percent form, we'd have to multiply times 100. And when we do that, we find that it's still very small. So it's actually 0.59% of the population have cystic fibrosis. Now, when it says assuming a Hardy-Weinberg equilibrium, how many newborns would have cystic fibrosis in a population of 10,000 people? Well, if this right here is the percentage of a population to actually have cystic fibrosis, well, then we would times that times 10,000. So, actually it'd be this number because this is in percent form. So we would take this with 3 zeros, 59 times 10,000. And we'd find about 6 people or so would actually have cystic fibrosis out of a population of 10,000. Okay. Now here, the ability to taste PTC is due to a single dominant trait. So tasters, dominant. You sampled 215 individuals in a biology class and determined that 150 could detect the bitter taste of PTC and 65 could not. So out of the 150 who could taste, they're going to be either homozygous dominant or heterozygous, and the 65 are homozygous recessive. What is the predicted frequency of the recessive allele? So that's asking us for Q, and then the predicted frequency of the dominant allele is P. So let's go ahead and solve for that. We know our recessive individuals, so that's 65 divided by our total, which is 215. This is going to be our Q squared. So we get about 30% of our population are non-tasters. So if we take our square root of this, so we find that when we take our square root, our Q is equal to 0.55, and then our P would be equal to 0.45 because P plus Q is 1. And so when I find this question here, 0.55, and P is equal to 0.45. Now, in a population of 10,000 people, how many people would be heterozygous? So here they're just basically asking for P squared plus 2PQ plus Q squared equals 1. Well, we already know our Q squared, our homozygous recessive, is 0.3. Our P squared is 0.45 squared. And that's equal to 0.2, or 0.20, and then 2 times P times Q is equal to 0.495. If you add these up, it's approximately 1. So when it's asking out of 10,000 people, here with 10,000 people, so 10,000 times about 20%, so 2,000 people would be homozygous dominant, and I would take 10,000 times 0.49.5%, so about 4,950 people would be heterozygous, and then I would find 30% of 10,000, and I'd find about 3,000 people would be homozygous recessive. Now we see this is not totally 10,000, and that's just from slight rounding. And now on to our very last problem with sickle-cell anemia. So sickle-cell anemia is an interesting trait. Normal homozygous individuals are homozygous dominant, and they are easily infected with the malaria parasite. And so in areas where there is malaria, they would have low fitness. And then individuals homozygous for sickle cell have cells that collapse easily, and they have trouble carrying oxygen. So they also would have low fitness. So now individuals who are heterozygous for the condition have some sickling of red blood cells, but generally not enough to cause mortality. In addition, malaria cannot survive well within these partially defective red blood cells. Thus, heterozygotes tend to survive better than either of the homozygous conditions. So if 9% of an African population is born with a severe form of sickle cell anemia, so right away I'm going to write this down. 9% is equal to 0.09, and that's going to be percent of my population, which is the number of individuals who are homozygous recessive, and that's my Q squared. What percentage of the population will be more resistant to malaria because they're heterozygous for sickle cell? So I have my Q squared, and when I take the square root of this, I find that Q is equal to 0.3. P is equal to 0.7 because P plus Q equals 1. And now they're asking for my heterozygote. So 2 times 0.7 times 0.3 is equal to 0.42, where about 42% of the population are going to be resistant to malaria and therefore have a higher fitness.